Thank you, Chairman, and good afternoon, everyone. First, I want to thanks for carrying the kind invitation and providing the opportunity to present our work here. And I'm Yikang Zheng, come from Institute of Geology and Geophysics, Chinese Academy of Sciences. And our former group leader is Professor Rongshu Zheng. Maybe someone have known him. He has been involved in some European and China collaborative CCS projects several years ago. And today I want to present some results we did in the geophysical monitoring in the Zhenghua CCS demonstration project. It's located in the Ordos Basin. And my presentation will cover 4 parts, and the first one is the motivation behind this project. The Shenhua CCS demonstration project is China's first pilot-scale demonstration for CO2 storage in deep saline aquifers. Its purpose is to inject 300,000 tons of CO2 captured from the core liquefaction plants nearby. And during this project, the 3D seismic is implemented to identify the reservoir, and time-lapse VHT surveys are conducted to track the subsurface changes. And as our group is focusing on geophysical methods, so what we can do in the monitoring? Our job involves the 3 phases, and pre-injection we try to identify the storage formation from 3D seismic images, and during the injection we try to track the CO2 plumes from the time-lapse VSP data, and post-injection we try to use reservoir simulation to evaluate the storage safety in the future. The first part is the reservoir identification from 3D seismic imaging. In each part, we developed some new methods to solve the practical applications. In the reservoir identification, the problem we met is that the usual method, such as the grain level co-occurrence matrix method, is only designed for 2D seismic data. It struggles with the 3D seismic volumes. Although we have some solutions such as the voxel co-occurrence matrix method, it basically implements the grain level co-occurrence matrix in the 3 different directions, but it will have the directional distortions in the real data application. Thus, we developed a new method called the high-dimensional co-occurrence matrix to avoid the directional distortion and to better identify the formations for CO2 storage. And this is the initial results from the 3D seismic images. And the red dashed circles is the depression phenomena of amplitude. It implies the existence of the channel, which is regarded as the desired storage reservoir for CO2. But due to the limitation of the conventional method, it is difficult to identify the horizontal distribution of the channel directly. Thus, we applied our new method and compared the previous VCM methods. The HCM method we propose provides more details for the identification for the reservoirs. And this is the final results. The HCM can reverse clear channel boundaries, and the HSM's multi-directional accesses suppress the noise and enhance the interpretability. Okay, and from the final images, we can map the channel's deposits at the depth of 1900 to 2000 meters, which is the interface of Shihezi and Shiqianfeng formations. And the extract channel features also indicates the ancient glacial systems, which is taken as ideal for the CO2 storage due to their porosity and permeability. The Logan data also confirmed the HCM results and the sandstone layers, and the AMR analysis validated the petrophysical properties. This integration ensures we are targeting geologically stable formations. With reservoir identified, we did also some time-lapse analysis to track the CO2 plumes during the injection. In Shenhua CCS demonstration project, 3 VSP surveys are conducted, and during the injection, they also did some hydraulic fracturing to enhance the injectability. So it also makes the time-lapse analysis more complex. And this is the VSP seismic geometry. It includes both the walkaway and the walkaround surveys. And we did some conventional seismic imaging to track the CO2 images. And recently, we also did some new inversion method to find the CO2 plumes directly from the velocity profiles. And we use it here is called the travel time wave equation travel time inversion. This is the objective function isolated from the dynamic mapping of travel time differences. And this can be taken as the intermediate results between the travel time tomography and the full waveform inversion. And because the location of the receivers is above the targeted CO2 injected reservoir, so we also combine the direct waves and the reflection waves to do the inversion. This is the synthetic test. We can see that by using this new inversion method, we can obtain more accurate velocity model, and by using the velocity profiles in imaging, it provides better results for the subsurface reflectors and scatters. In the real data application, we use the walkaway 91 for the inversion, as it has the best matched repeated source location. Okay, this is the inverted P-wave velocity, and this is the velocity differences. It can be used to identify the plume migration pathways. These changes correlate with the CO2 distribution and confirming containment within the target reservoir. After the injection, we also use some reservoir simulation to predict the plume behavior and evaluate the long-term safety. And using seismic and wire data, we built a geological model with injection points in the formations. Key parameters include the porosity, permeability, and the injection amount of CO2. And the simulated pressure changes. Here is the solid lines and are compared with the observed data shown by the dashed lines. The match validates our model. This accuracy is important for the predicting. Okay, this is the simulation results. It shows CO2 saturation spreading slowly from the injectors. After 50 years, the plume stabilizes confined by the cap rock. No overall leakage risk were detected from the simulation results. Now we also want to, because in the simulation we just use the pressure data, we also want to integrate the seismic data. And a problem we met is that the simulation process using the Eclipse or tough software is quite time consuming. So we also developed some deep learning methods to solve this problem. This is the network framework we proposed called the swing transformer. It is different from the conventional UNet as it added the attention mechanism into the neural network. And this is the initial results. The training curves shows the swing transformer's stability is better than UNet. Our model can achieve lower validation error, and this is can be a useful tool in our joint emerging workflow. Okay, the last part, a simple conclusion of what we have done. Okay, pre-injection, we proposed an HCM method to effectively identify the suitable reservoirs for CO2 storage. And during the injection, we used the time-lapse VSP reflection velocity emerging to track the CO2 plumes. And post-injection, and we establish an appropriate reservoir models with the seismic constraints to evaluate the safety in the future. And what we are working on is to trying to combine the geological interpretation and the seismic emerging and reservoir simulation to establish a joint workflow in the CCS monitoring. Okay. At the end, I'd like to share a message from Professor Zheng, who has participated in several successful European and China joint research projects in the past. And if possible, we are glad to find some cooperative opportunity in the CCS projects. And our institute offers annual international scholar funding programs for joint research, academic exchanges, and innovations in the fields like CCS and geophysics. And if someone have interest, we warmly invite you to visit us in Beijing. Okay, that's all. Thank you.